Hey guys, this section is about exponential models, and it is kind of a tough section. It's all application problems. We're going to be using this formula called the continuous growth formula. I wrote it a little bit big over here so you can hopefully see it better. It's A of t equals A naught is how it's pronounced, e to the RT. And let me just kind of go through the pieces of the formula. So A naught is the initial value, so this would be like the population at t equals 0 or the amount of money invested. E is our friend 2.718, etc., that irrational number. R is the rate. T is the elapsed time. The rate, by the way, if the rate is greater than 0, it's going to be a growth equation. If the rate is less than 0, it's going to be a decay equation. And then A of t is the amount after some time t, the output. So one of the things that makes these problems hard is that there's a lot of information in there. There's usually 5 pieces of information in these problems, and 3 of them are A's and 2 of them are T's, and so telling them apart can be a challenge. And so what I have is kind of an approach to solving them. So let me kind of go through the steps, and I think this pretty much works on most of them in the section that I am remembering. I think there's a couple where we kind of deviate from this plan, but I'll show you those when we get there. So step 1 is to identify all the known and unknown quantities. And so I have the notes set up with sort of these 5 things, that we're going to have a t for the rate and an a for the rate. So there's going to be some ordered pair in the directions that kind of gives us information about at this time there's this much, and we're going to use that to solve for the rate traditionally in these problems. A naught, again, that was our initial quantity, so if we're going to identify that. A final is kind of A of t, so it's the amount after the time has elapsed, and t is the time elapsed. So these are kind of the 5 things we're going to look for, at least in these first few problems. And once we have those identified, we're going to use step 2 is we often have to find the rate. And so we'll use that ordered pair that I talked about up here in the growth equation and use that to solve for R. And then once we have R, we can use that to solve for whatever it is we're looking for in the final step of the problem, which could be any of the 3 quantities. So this first example is actually really easy, and this one gets posted a lot, but it's suppose the population of a city is given by the equation P of t equals 30,000 e to the 0.07 t, where t is the number of years from the present time. A lot of words. How large is the population now? Okay, how large is the population now? That would be A naught. That's like the starting amount. So all you gotta do is look at the equation and see what A naught is, and that's the answer to that one. So that's the easiest question in this section. And then after that, they get quite a lot harder. So move on to those. Okay, so number 2, in 5 years, 30% of a radioactive element decays, find its half-life. So let me explain what a half-life is, just to kind of help figure out how to figure out the problem, and probably what radioactive decay is actually too. So if you have a radioactive element, it spits out a particle, and it's called radioactive decay, and that's that radiation that can be a problem. And so as an element sort of sits there and ages, it's going to decay. And a really common one is carbon-14, so that's the one that they use for radiocarbon dating to figure out how long ago something died. And so the idea with that is that once you die, you stop breathing, and you stop taking in this particular isotope of carbon, carbon-14, and it's radioactive. So once you stop taking it in, because you're dead, the carbon then starts to decay. So if they measure the carbon-14 left in the organic material after some number of years and compare it to the environment, it's going to be less. And so if you know the rate of decay, then you can figure out how long ago the thing died. And so that's sort of what radioactive decay is. And what the half-life is the amount of time it takes for half of that element to decay. So that's probably longer than it needed to be, but there's that. That was my physics degree coming out a little bit. So in this problem, we have in 5 years, 30% of a radioactive element decays, find its half-life. So one thing that kind of strikes me about this is that they didn't actually tell us how much we started with. Like, we just know it's 30% of something. And so in that case, I just make up a number, and 100 is a really good number to make up because it's really easy to take 30% of. So if 30% of the radioactive element decays, it's going to be 70% is what's left. So I'm calling this 100. It can be 100 whatever, 100 whatever you want, grams, whatever. But I'm just making a number. And you'll see that when we divide, when we start to solve this, we'll divide. And so it wouldn't matter if I'd picked 10 or 50 or whatever, the ratio is going to be the same. So you might as well pick an easy number like 100. So anyhow, 30% has decayed. That means 70% is left. So, and remembering that our continuous growth formula, T is our input and then A is our output. So T and A this way. So we got 5 years. We're going to have 30% less, which would be 70 grams or whatever. Find its half-life. Okay, so that sounds like we're finding a time, but we don't know the amount final, but that's okay because we made up this. And the half-life would be when there's 50, say, grams of this stuff left. So in this case, T is the thing that we're trying to figure out. So that's what we're trying to solve for. So the second step, now that we've identified all our stuff, is to set up the growth equation, or in this case, a decay equation, and find the rate, because we don't know rate yet. So what we'll do is we'll use this ordered pair right here, and we'll say, actually, let me write down the formula. So A equals A naught E to the RT. So that's what I'm plugging into. So the amount after some years is going to be 70. And the initial amount was 100. Was our A naught. E to the rate we don't know. And T is 5 years. So then the first thing I do is divide over this 100 right here. And then what that does is makes this 0.7, and that's why I was saying it doesn't matter what numbers I pick. If I picked 1 and 0.7, I would have got the exact same thing. So pick something easy. And then we write this as 5R, just so it looks a little bit better. And then we're solving an exponential equation, so what we want to do is log both sides, and since it's a base E, we definitely want to use natural log because that will make it easier. So then I have natural log of 0.7 equals 5R ln E. And then remember ln E equals 1, so that piece just drops out. And then I can divide over the 5. And that gets me R. And so R, if you put it in a calculator, is about negative 0.0713. I usually put it, when I'm actually doing the calculation, I usually put this exact value in. I don't switch to a decimal as much as possible. Some of these problems, the decimal places, like they're going to have fairly large answers. And so if you round, you can actually change that answer enough to then get it wrong in the computer. So try to use the exact form as much as you can. So now that I got rate, I'm supposed to find the half-life, so now I'm solving for T. So now I'm going to say 50 is the amount final, 100 is the amount we started with, E to the R. And then what I do is I just call this thing big R. And I do that so that right here I could just write big R when I'm doing this on the board and not make it look more confusing. So big R is just going to stand for this chunk, and I'm going to do that for the rest of the lecture. It just makes it cleaner for solving, and then I put this back in at the end, which is actually a pretty good technique for making things look simpler so you make fewer errors. And then the time is what we are trying to figure out. So I divide over this 100. And this little solve I'm doing, you'll be really, really tired of by the end. It's really repetitive, and it ends up not being too terribly hard. And then we'll take the log of both sides. Once I do that, I can bring down the RT. ln 0.5 equals RT ln E, and again, that's 1. And so then I can divide both sides by R. And then that gets me T. So this would be ln of 0.5 over where is it? There it is, ln 0.7 over 5. And then another and better way of writing that is 5, so if I bring this over and flip, 5 times ln 0.5, I should probably do parentheses, over ln 0.7. And then if you chunk that in a calculator, I got to one decimal place about 9.7 years for the half-life. Okay, so this next one is also a radioactive decay problem. So only 15% of the carbon-14 in a wooden bowl remains. How old is the bowl round to the nearest year? And the half-life of carbon, they tell us, is 5,730 years. So I'm going to do that thing where I just let the starting amount be 100 again because it's easy. So that if 15% is left, my final amount is 15 then. Our time to find our rate, because we have the half-life, so I know in 5,730 years, there's going to be 50% of the stuff left, so we'll call that 50. And again, we're solving for the time. So then we'll set up our first equation with the rate information. So this will be, we're going to have 50 left when we start with 100 E, and then our rate is what we don't know, and our time is 5,730. So divide the 100, that drops out, 0.5 equals, this will be e to the 5730 t, natural log both sides. And then this comes down front, ln e drops out again. So this little solve gets pretty repetitive by the end. And then divide both sides. Oops. As a shortcut, the rate on these half-life problems is going to be natural log of 0.5 over the half-life. And you'll see there's kind of this pattern that emerges with how the rate is. It's going to be, natural log of whatever the percentage was. I think the last one, right, was 0.7 over the time it took to happen. So you can kind of shortcut finding that rate a little bit. If you can remember this, you're welcome to use it. And so for half-life, it's 0.5, but if it had been 70%, this would be a 7. But it's basically the ratio of the natural log of the percentage that is left over the time it took. Anyhow, so once we find that, again, that's what I'm going to call big R. And then I'll set up the equation to solve for the time. So we got 15% left. We started with 100. E to the, I'm just going to call it big R, and then T. So dividing, I get 0.15 equals E to the RT. We do our natural log again. RT comes down. And then ln e would drop out because it'd be a 1, and then just divide the R over. And so again, I'm going to do that little flip, and then that means this will be, with the rate filled in, 5730 times ln of 0.15, should do that, over ln 0.5. And so if you successfully get that in the calculator, I think I got 15,683. Okay, the population of Seattle is 662,400, and is expected to double every 25 years. I think I'm making that up, so don't worry. And how many years will the population be? 2 million. Okay, so they gave us in 25 years, it's going to be twice this amount. And so this amount is my starting amount, so that'll be our 662400. And then in 25 years, we're going to have twice that. And so that is 1,324,800. The amount final we're going to be looking for is 2 million. And again, how long until it happens? So we can do the rate. And so since this is doubling, I'm going to not write out, just for the sake of space, I would put the 662,000 on this side, the 1,300,000 yada on this side. I'd divide, and it would come out to 2, right? Because it doubled. So I'm just going to do that, and not write all that. So that'll be e to the 25, and then we're looking for r. And then I natural both sides, as always. 25 comes down, ln 2 equals 25r, and then ln e again is just going to become a 1, divide over the 25. And so there we see the ratio, so it's doubling, so it's a 2 over the time, and that's going to be our big R. And then this time I have to actually write the numbers. So 2 million, if that's the right number of them, equals 662,400 e to the big RT. So we divide over this. And I got 3.019 equals e to the RT. I can natural log both sides. That lets RT come down in front. Again, ln e drops out, divide over r, and then put that in the calculator. And I got t equals 39.85 years. Number 5, bacteria culture grows according to the formula. And this is the exact same formula. They're just using P for population instead of A for amount. So I didn't change them over here. If it takes 14 days for the culture to double in size, how long will it take to triple? So much like the Seattle problem. So we don't know how many we have, so that's where I just make up 100. But we know in 14 days, there's going to be 200. And we're looking for how long until they triple. And so if I kind of do set this one up, I get 200, 100 e to the 14, r. And then there's our 2 because it's doubling, e to the 14r. Log both sides. That's our 1, bring that over. So doubling in 14 days, that's our big R. And then once we have that, we just do the same thing again, we solve for t. So now it would be 300 and 100, so I'm just going to write 3 because it's going to triple. E to the big RT. Probably getting where you can do this part in your head and know where it's going to end up. So ln3 equals RT, that drops out, so that's our over R. And again, if we plug that in the calculator, the 14 would be on top, ln2 on the bottom. I got about 22.19 days. Okay, and these last couple kind of diverge from that little template we've been doing. They're actually a little bit easier, I think. So the number of airline passengers in 1990 was 240 million. The number of passengers traveling by airplane each year has increased exponentially according to that model, and where t is the number of years since 1990. So what that means is when we get an answer, we have to add that onto 1990 to find the year. In what year is it predicted that 6 million passengers will travel by airline? So that just means we're going to get 6 million out, and we're just trying to figure out what the time is. So I'll get that set up here. 6 million equals their equation, 240 times 1.025 to the t. And so before I log anything, I always want to divide this out. So do that on both sides. And that will be 2.5 equals 1.025 t. And then I will natural log both sides. I could do log base 10 too, wouldn't really matter on this one. And that brings t down front. And then I can just divide over the natural log of 1.025, and that solves for t. And so when I put that in the calculator, I got t was going to be about 37.1 years. But that's not what it asked. It asked him what year is that predicted to happen. And so remember, this is our year since 1990. So we have to go 1990 plus 37. It's going to be somewhere in February, it looks like. 7, 2, carry the 1. So 2027. And last one. So find the time required for an investment of $2,000 to grow to $5,500 at an interest rate of 7.5% per year, compounded continuously. So remember, our compounded continuously formula from earlier in the chapter was the amount will equal the principal e to the rate and then times time. So, and this is our principal, how much we put in, how much we get out. So this will be our 5,500, can't say that, 2,000 on this side, E, rate we know 7.5%, so that's 0.075, and then T. And then here we'll just divide over the 2,000. And that will give us 2.75 equals E 0.075 t, and then natural log both sides, and this time definitely because of the E. And this comes down front. And then there's that ln that drops out again. And then from there, just divide over the 0.075 on both sides. And that will get you t. And I got t to be about 13.49 years. And that concludes exponential models.